Welcome to the MOOC on Discrete Mathematics. This is the second lecture on mathematical logic. We will continue with our discussion of propositional calculus that we started in the last class. In the last class, we talked about the Boolean functions on n variables, and we saw that such functions can be synthesized using AND or NOT gates. These are logical connectives. Using these logical connectives, we can synthesize any Boolean function on n variables. Therefore, this set of logical connectives is called a complete set of connectives. We found that this is by no means the only complete set of connectives. We find that and NOT also form a complete set of connectives. Similarly, OR and NOT also form a complete set of connectives. NAND is also a complete set of connectives on its own. NOR also forms a complete set of connectives on its own. So, a Boolean function on n variables can be synthesized using any of these sets. Some of these logical connectives can be expressed as logic gates. An AND gate is drawn like this in a circuit diagram. So, an AND gate has two inputs x and y, and the output is x and y. The output is 1 if and only if both the inputs are 1. An OR gate is represented in a diagram in this manner. Where the inputs are x and y. A NOT gate has only one input, let us call it x, and its output is the negation of x. A NOR gate, which is a negation of OR, is drawn in this manner. X and y are the inputs. The output is x nor y. A NAND gate is an AND gate followed by a negation. An XOR gate, which produces an output of 1 if and only if the inputs are not the same. Is denoted like this. Therefore, using these logical gates, you can convert a Boolean expression into a circuit. For example, if you have a Boolean expression of this form, we have the signals x1 and x2. They can be odd using an OR gate, the output of which can be ANDed with x3. So, this is the circuit diagram corresponding to this Boolean expression. So, what we know is that any Boolean expression can be converted into a circuit diagram using AND or NOT gates, using either the sum of products form or the product of sums form. You can have an equivalent circuit diagram created using only NAND gates too, or NOR gates. NAND and NOR are universal logic gates. Because every circuit can be synthesized using only one of these. and these are the only universal logic gates. This we proved using the following argument. Suppose H is a universal logic gate, a Boolean function H with two variables. If this is a universal logic gate, then when both the inputs are 0, the output of H will have to be 1. Otherwise, we will not be able to use H to synthesize a function like NAND. That is because when you have a circuit made up only of H gates, and when both the inputs to the circuit are 0, then the circuit will have only zeros in the inside, if H of 0, 0 were 0. Therefore, to be able to synthesize every function which produces 1 when both the inputs are 0, H of 0, 0 will have to be 1. Similarly, H of double 1 will have to be 0. Therefore, we have only 4 possible functions. Of these, 2 are the negations of the inputs. Therefore, the 2 remaining functions are NAND and NOR. These are the only universal logic gates. Now, let us consider implication. The implication is a 2-variable Boolean function with this truth table. When both the inputs are 0, the output is 1. When x is 0 and y is 1, the output is 1. When x is 1 and y is 0, the output is 0. And when both the inputs are 1, the output is 1. So, what it means is that x implies y is false if and only if x is true and y is false. Or we can say x implies y is logically equivalent to the complement of x y bar, which by De Morgan's law is x bar plus y. So, we find that x implies y is true when x is false or y is true. In the case of an implication, x is called the antecedent and y is called the consequent. So, what we have seen is that if the antecedent is false, the implication is true. On the other hand, if the antecedent is true, then the implication is true only if the consequent is true. This has interesting consequences. We can derive essentially any statement from an antecedent which is wrong. The legend has it that Bertrand Russell famously showed that if 2 plus 2 equal to 5, then Bertrand Russell is the Pope. His argument was this: if 2 plus 2 equal to 5, then we can subtract 2 from both sides, then we have 2 equal to 3. If we subtract a further 1 from both sides, we have 1 equal to 2. Therefore, we have 2 equal to 1. Then consider the set containing Bertrand Russell and the Pope. This set has 2 people, namely Bertrand Russell and the Pope. therefore the cardinality of this set is 2. But then we know that 2 equal to 1, therefore the cardinality of this set is 1. But if the cardinality of a set is 1, that set is a singleton set and it has only one member. Therefore, Bertrand Russell is the Pope. In other words, if the antecedent is false, then practically you can prove anything as the consequent. Therefore, we can judge an implication only when the antecedent happens to be true. Consider the implication x implies y. The implication y bar implies x bar is called the contrapositive of x implies y. Using a truth table, you can readily verify that x implies y is equivalent to y bar implies x bar. Every implication is logically equivalent to its contrapositive. Y implies x is the converse of x implies y. And x bar implies y bar is the inverse of x implies y. So, by what we have seen just now, the converse and the inverse are logically equivalent. Namely, y implies x is logically equivalent to x bar implies y bar. The implication P implies Q will be written in English as if P then Q. P is sufficient for Q, Q when P. A necessary condition for Q is P. Q unless not of P, P implies Q. P only if Q, Q follows from P. So, these are all essentially the same thing, they all denote the implication P to Q. The logical connective P is equivalent to Q, which is the negation of the exclusive OR, is usually written in English as P is necessary and sufficient for Q. P if and only if Q. Or P is equivalent to Q. Equivalence is true if and only if P and Q have the same logical value, either both are true or both are false. So, we have seen several logical connectives now. In an expression that uses many of these logical connectives, how would you parenthesize the expression if the parentheses are not already placed in it? For this, we have to use the precedence rules. The precedence rules commonly used are these. Negation has the highest precedence, which means you have to associate the negation symbol to the nearest variable first, and then NAND have the next preference. They associate from left to right, OR and NOR have the next precedence, again they are from left to right. Single implication comes next, but this associates R to left, right to left, and double implication has the least preference, which again has a right to left association. So with these precedences in mind, let us work out an example. Let us see how parentheses can be inserted in this expression. When an expression is given like this, first you should insert parentheses here because an has the highest precedence. After that, the precedence is for or, therefore you should parenthesize them in this manner. So this is the first parenthesis, this is the second one, this is also at the second level. Then at the third level we have implication. So this is the third parenthesization, and then the double implication, the two-way implication has the least precedence. So this is the last one. So this is how you would parenthesize an expression containing many of these connectives. Let us consider another expression. P implies Q implies R. When we discussed precedences, we said that implications have right to left associativity. Therefore, you will have to associate Q to R first and then an outer parenthesis. Similarly, when I have an expression of this form, P or Q exclusive or R, we find that the precedence is for this, therefore this is where you put the parenthesis first, and then the whole of the expression is put in a parenthesis of a lower precedence. So this is how you would parenthesize Boolean expressions. An expression is called a tautology. If its truth table has only ones in the rightmost column. For example, let us consider x or x naught. This evaluates to 1 for every assignment to x, which means x or x bar is true for every imaginable assignment. If you drop the truth table of it, in the rightmost column we have only ones. Therefore, this is a tautology. A tautology is a statement which is always true. Whatever be the truth values that you assign to the variables of the formula will always evaluate to true. The complement of a tautology is called a contradiction. For example, if you have x and x bar, you find that it evaluates to true for every possible assignment. It has only zeros in the rightmost column. Such a Boolean expression is called a contradiction, a statement which is always false. In the last class, we saw that two expressions E1 and E2 are logically equivalent if and only if their truth tables are identical. In particular, we saw De Morgan's laws. Let us see several more equivalences which will be useful for us to prove various statements. One is the identity laws. The identity loss states that P and 1 equal to P and P or 0 is equivalent to P. You can verify this using the truth table. For example, consider variable P and the logical function 1. P can take on values 0 and 1, and for any assignment to P, 1 takes on values 1 and 1. Therefore, P and 1 here would be 0 and 1. This seems to be identical to the first column, which is P. So, P and 1 is the same as P. Similarly, P or 0 you find is identical to P again, proving the identity loss. So, when you take the AND of P with 1, you get P itself, and of anything with 0 will give you the same thing. The next are the domination laws. Domination laws say that P plus 1 is equivalent to 1. Anything odd with 1 gives us 1. That is, 1 is a certainty, so something or a certainty is always a certainty. Similarly, P and 0 is 0. You can verify these using the two tables. Then idempotent laws. Idempotent laws says that P or P is P and P is also P. Double negation. Double negation asserts that the negation of a negation is the same as X. Again, you can verify this using a truth table. The negation of 1 is 0, the negation of 0 is 1, so this is identical to X, establishing the double negation law. Then the law of commutativity, which says that and or are commutative operations, namely X or Y is the same as Y or X. Similarly, X and Y is the same as Y and X. Then we have the associative law. Associative law says that the OR of A with the OR of B and C is equivalent to the OR of A or B with the OR of C. So, by extending this, we can take the OR of a chain of formulae in whichever order is convenient. For example, this is the same as this. So, you can parenthesize in whichever way when you have a long sequence of disjunctions. So, you can verify this using the truth table readily. Similarly, for the AND operation, A and B and C is the same as A and B and C. Again, you can verify this using the truth table. Now comes the distributivity. The law of distributivity in this form is familiar to all of you from arithmetics. That is, when we compare OR with addition and with multiplication, this is a familiar form of distributivity, which you can easily verify using the truth table. But there is another distributivity law which doesn't have an equivalent in the algebra of numbers. A or B and C is A or B and A or C, which means OR distributes over AND, the way addition doesn't distribute over multiplication in arithmetics. Then of course we have the familiar De Morgan's laws, which says that the complement of A or B is the complement of A and the complement of B. Similarly, the complement of AB is the complement of A or the complement of B. The absorption laws allow you to absorb Q in this fashion. P or PQ is the same as P. Similarly, P and P or Q is also the same as P. Then we have the negation laws. The OR of a quantity with the negation of itself is 1, the AND of a quantity with the negation of it is equivalent to 0. These are the negation laws. So, all these laws can be proved using truth tables. Now, let us consider a problem that is used to Smulyan, and you can find them in various textbooks. Let us say there is an island. On this island there are only two kinds of inhabitants, knights and knaves. Knights speak truth and only truth. Knaves tell lies and only lies. But you cannot distinguish who is a knight or who is a knave, all of them look alike. Let us say we encounter two persons, A and B. So, their appearances do not disclose whether they are knights or knaves. You will have to figure out that from what they say. Let us say A says B is a knight. And let us say B says the two of us are of opposite types. Then the question is, what are A and B? So, let us try to solve this problem by forming propositions. Let P denote the proposition A is a knight. Let Q form the proposition B is a knight. Now, what does A say? A says that B is a knight. So, A asserts Q. So, if A is a knight, which means if P is true, then A would speak only the truth and this would be true. And if A is a knave, then A would tell only lies and this would be a lie. That is, if A is a knight, which means if P is true, then Q also would be true. On the other hand, if A is a knave, which means if P is false, then Q would be false. Therefore, we have P if and only if Q. So, this is one conclusion we have. Now, from what B has said, we can conclude that B is a knight, which is if and only if Q. This is true if and only if what he said is right. Now, what did he say? He said that both of them are of different types, which would mean that either P is 1 and Q is 0, or that P is 0 and Q is 1. In other words, either A is an ith and B is an if, or A is an A when B is an ith. So now we have this logical equivalence, that is Q is true if and only if this is true. Therefore, the AND of the two logical statements is what we have. P if and only if Q, and Q if and only if PQ bar plus P bar Q. So let us try to simplify this expression. Let us see if we can figure out what P and Q are from these. Now P if and only if Q can be written using and or and not in this manner. This is true if and only if both have the same logical value, which is possible if both are true or both are false. On the other hand, if Q is true, then this will have to be true. That is, if B is an ith, then what he said should be right, which means either A is an ith and B is an if, or A is an A when B is an ith. Otherwise, Q is false, in which case both are of the same type, that is either both an ith or both an ifs. So this is the sum total of the two statements. The AND of the conjunction of the two statements is what we have taken. That is, this we concluded from the first statement, and this we concluded from the second statement. Therefore, both of these conclusions must be right. What does that entail? Let us try to simplify these expressions. We have P Q Q bar. By taking the AND of Q with P Q bar, by associativity and commutativity, I can flip Q and P and write this as P Q Q bar, and then I have P bar Q Q, that is from the first conjunction. From the second conjunction, we have P Q bar Q and P bar Q bar Q bar. Let us simplify this further. So this is logically equivalent to Q Q bar is 0, so this is 0 here. P and 0 is 0. Q Q is Q, therefore we have P bar Q here. Q bar Q is 0, then we have P and 0, which is 0 again. And then P bar Q bar is Q bar, so we have P bar Q bar, which is then equivalent to PQ or P bar Q bar and P bar Q and P bar Q bar. This can be written as PQ or P bar Q bar, and from the second term, if you take P bar outside, we have Q plus Q bar on the inside, which is because Q plus Q bar is 1 and P bar and 1 is P bar. Now if you take P bar inside, from the first term we have P bar PQ, but since P bar PQ is 0, we have 0 here, and then from the second term we have P bar Q bar, but P bar is P bar, so we have P bar Q bar, which is P bar Q bar. So we find that this logical expression reduces to P bar Q bar. What does that say? It says that A is an if and B is an if. Both of them are naives. That is what we conclude from the logical expressions. Let us consider one more such problem. Let us say in this case, person A says at least one of us is a knave. And suppose B doesn't say anything. Then let us see what A said. If A is a knight, if P stands for the statement that A is a knight, in which case what he said is right. Now what did he say? He said that at least one of us is a knave. Then either both of them are knaves, or A is a knight and B is a knave, or A is a knave and B is a knight. It is not possible that both of them are knights. For at least one of them to be a knave, this is precisely how the situation should be. Now, what does this mean? This is logically equivalent to saying that if P is true, then the quantity in the bracket is true, or if P is false, then this quantity in the bracket is false. But what is the negation of the quantity in the bracket? We want to negate P bar Q bar plus P bar Q plus P Q bar. To compute the negation of this, let us first simplify this expression. We can write this as P bar times Q bar plus Q, and that odd with PQ bar. This is what we want to negate. But then Q bar plus Q is 1, therefore this is the negation of P bar plus PQ bar, which by De Morgan's law is the negation of P bar and the negation of PQ bar. But double negation of P is P itself, and the negation of PQ bar by De Morgan's law is P bar plus Q. If you take P inside, we have PP bar plus PQ, which is equivalent to 0 plus PQ, which means we have PQ. So the quantity within the bracket when negated will give us PQ. That is, this is PQ. Therefore, this expression reduces to PP bar Q bar plus PPQ bar plus PP bar Q plus P bar PQ, which is 0 for the first expression, PQ bar for the second, 0 for the third, and 0 for the fourth. The OR of these four quantities would be PQ bar. So what we have concluded is that the logical statement that we had is equivalent to PQ bar, which means A is a knight and B is a knave. That is the conclusion we have drawn. So that is it from this lecture. Hope to see you in the next. Thank you.